All right, so good job on the test last week. It went, I think, slightly better than the first test for those of you that are normally in attendance here. Average grade on the test was about the same as the first one, but still that's all pretty good. Average grade is about 80%. So those grades I posted yesterday. If you have questions, I can let you know like which topics you had problems with, what areas to restudy on prior to your final, that sort of thing. But in any case, we have 5 weeks here. This is week 11, 12, 13, 14. I think we have 4 weeks in class regular and then a week where we have exams, and ours is on a Tuesday night. I did get an email. I know it says in the syllabus, and I'll post this. It says in the syllabus that our exam is on Tuesday, May, whatever that Tuesday is. Tuesday, May 3rd, May 2nd, that Tuesday at the start of May, during exam week from 7 to 9 p.m. or 7:10 till 9 p.m. in a room to be determined. It was determined that we are going to be in here, so that's easy to remember, because it's a uniform exam time as opposed to meeting at our regular class time, because there are about 15 sections of this course and everybody's taking the exam at the same time. And sometimes they switch rooms on people if there are several sections that met in the same room. But lucky for us, we are in here and we don't have to go anywhere strange suddenly for our final exam. And I will put that on Canvas and in the iMath section just so you remember where our exam is, because it doesn't physically say in the syllabus, but it is here, which is easy to remember, even though it's not at our regular class time. So what we've got these last 4-ish weeks of class is we're going to be working on angles and circles and triangles, trigonometry. So there's a whole bunch of different aspects to trigonometry and how it's used. Some's with triangles, some's just with angles, whether or not they're in triangles, but the same measurements persist when we're talking about how do I measure angles. It's a little bit challenging. There's simple questions. This is just Module 7 Investigation 1 here. So which of the angles has the smallest measure and which is the largest measure? And that's a simple question. Like, okay, you've been in school, you've seen angles for a long time. But if you try to think about what does it mean, the measurement system that we use for them? So of angles A, B, and C, first of all, which is the smallest angle? A. And the largest angle? B. And we have a variety of ways to measure these angles, different unit systems. Degrees and radians are the most familiar ones. There's also gradients, which if you ever had one of those calculators where you switch between 3 modes, it says deg, rad, and grad. It's just, gradients I think they're a French unit, but they aren't really used in a lot of places. It's just to be nice round numbers. Something like metric equivalent of degrees, I guess you'd say. But in any case, if I say, well, what's a degree? It's like, if you try to describe what is a degree? If I say this angle is 30 degrees, what is a degree? How do you measure, if I say, oh, this is 6 inches, you can say, oh, that's like this. Or 2 feet is like that, or a meter is like this, or this. But if I were to describe what's a degree, anyone have a thought on how you describe a degree? Yeah.
It's like a measurement of rotation.
Okay, yeah, we've got measurement of rotation. So we can measure rotation, but you can also have stagnant objects and say that they have like a certain degree measurement. Like these angles all have degree measurements that go along with them. But it's not something that's like a length measurement where you can have a tape measure and measure a length that you see. The issue is I can have 2 angles that are the same degree measurement or whatever units you're using. Like degrees and radians are just 2 different unit systems, like miles and kilometers. It's 2 different ways to measure the same thing. They have different bases of where they came from. But I can have, let's say a 30-degree angle maybe looks kind of like that. I usually put arrows on the end just to indicate this isn't just a little wedge, like pieces of paper. This is just the idea of something that could go as far as I want, but that said, it could be something like that, or it could be bigger, and maybe I draw one of these lines really long, but they could have the same angle measurement. Right, so I'm talking about how far apart these lines are, but not how far apart as in inches, because obviously I could measure that in a bunch of different places too, and I could measure it with like straight lines, I could measure it with curves, so that doesn't make, it's not a distance in that sense. So if I say something has a 30-degree measurement, it's all relative to something else, right? So 30 degrees, like in terms of how big is 30 degrees, it's not like this big or that big or this big. It's not a size in that sense, it's all a relative to how big something could be, right? So it's kind of this weird, like, well, we have this measurement system, but it's kind of like percents in a way, in that you know how big it is, not based on its physical lengths, but we know how much it is based on what portion it is out of something larger. So if I say, oh, this is 30% of something, like, oh, okay, so if that's 30%, then I could figure out how much 100% is. But this isn't 30% of something. If it's 30 degrees, I'm talking in degrees, what's a larger number that you maybe, and there are several answers to this, that you maybe think of this relative to? Like, why can I imagine that maybe that's 30 degrees? What's a larger number of degrees that it's possibly easier to compare it to? And like I said, there's several different numbers you might be using. Well, one number that people use a lot with reference to degrees, 90 degrees. 90 degrees it's just another degree measurement, but it's maybe easy to picture because what's 90 degrees, right? Nice square corner. So if I say, well, if this is 90 degrees, then 30 degrees is a third of that. So maybe that's a little bit big. Maybe that's like 40 degrees. If I take 90 degrees, which I can imagine a nice square corner pretty easily. So this is a third of that. Or 45 degrees would be half of that. And so you can think relative to a 90-degree angle, how big is it? Larger or smaller? But still, that's just relative to a 90-degree angle. They're just interrelated measurements where we know how big one thing is compared to another. And so there are some numbers that are nice and easy to picture how big they are, and others that we just think of as portions of those, unless they're just, like 30 you use all the time. But if I said something like, oh, it's a 54-degree angle, you probably would say, oh, I know exactly how big 54 degrees is. You might think, oh, that's a little bit bigger than 45, or a little bit more than half of 90, or something like that. Or if we're talking about angles more like this angle B here, obtuse angles, maybe I'd think about, oh, maybe that's 130 degrees. Well, I know it's more than 90, but it's less than 180. Just some like key numbers to know in order to describe how large it is, because again, 90 degrees is something you can picture, 180 degrees is something you can picture, and we're looking for a portion of that or something that's in between. And we can have larger angles. It's kind of hard to talk about angles that are more than 180 degrees in terms of just a stagnant picture, because you can always then measure a smaller angle. But if we start talking about, as you mentioned, rotations, things that have a motion involved with them, not just two fixed points, maybe I talk about, well, I start here, and the other end of my angle I get by rotating this direction. So this is a very large angle, but that's something that, in terms of moving by a certain number of degrees, that's something that happens all the time, even though if I look at, well, how big is this angle? Why don't I just measure the small part? You can. But if I want to talk about something that's spun around, I want to talk about how far it's moved, but not in a number of feet necessarily, or a number of centimeters, or a number, like a length unit. I might want to talk about how far it's moved as a number of degrees or some other unit. So when we talk about angle sizes, all of the units we're using are for the angle size are relative to something. And so degrees, in terms of this rotation idea, we have like 90 and 180, but if I were to go all the way back to where I started, how many degrees is all the way around? If I were to like have my starting and ending point both the same. I start here, rotate all the way around, and end up back where I started. How many degrees is that? 360. All right, so degrees I can think of within, something for less than 90 degrees. I can think of, oh, it's like between 0 and 90. And you can think of these different amounts based on maybe 90, 180, or 360. And those numbers are, they're large numbers, but if that's all I'm talking about within one circle of rotation, then I can deal with subdividing those. And the reason that 360 is a very nice number to use, even though it's like, why didn't we just pick 100? That's kind of where gradients come from. Gradients picked 400 as the all the way around. That way I can have 0 to 100, 100 to 200, 200 to 300, nice, easier numbers to count. Right? It's just a different measuring system. 360 it seems like a weird number, but I will say this for it. It has a lot of divisors, just like 36 does. Like you can divide it by 2, 3, 4, 6, 10, like all these, not 10, 12. All these numbers you can divide it by, so you can split it up into pieces pretty easily, which is why 360 is nice to work with. It's also why a dozen became a unit of measurement for selling stuff in. Like let's say you go to the market in the 1500s and you buy a dozen eggs. Well, if you have a family of 2, 3, 4, or 6, you can split them up evenly among everybody, and it's fine. If you bought 10, which seems like a nice round number, doesn't work nearly as nicely. So 12 is a good number. 36, same sort of reasons. Some of the reasons our measuring systems came out the way they did and units of measure are the way they are is because they're easy to divide up. And 360 is one of those. It's easy to divide up, even though it seems like a strange number. It's hard to count by. So if you keep spinning around and are counting your angles, like 360, 720, 1080, I'm losing track of stuff. But I mean, it's, if you have a calculator, it's just as easy to do as anything else. But it's all just a relative unit of measure. And one of the reasons it's 360 is because, like I said, it's easy to divide by that. There's also lots of ancient, days of the year are 360 in old calendars because it was kind of like, yeah, this seems about right. Easy to split up into months or whatever you wanted to have, seasons. But in any case, point of all this is angle measurement all has to do with relative to something else. So it's about, let's define how much makes a whole, whether that's like a full circle or like a square corner, whatever your whole is, and then define pieces of that based on relative size or relative amount of that space that they cover. So this 7.1 investigation goes through a lot of sort of those thoughts. I don't want to go through all of this, but just whether I'm thinking of these as just a couple of lines, rays, that are spread apart from one another by a certain portion, or that these are, as we're going to use for measuring purposes, oriented where the vertex of the angle's in the center of a circle, and then I can see along the circle these sorts of things that we draw to indicate that we're measuring angles. We can actually talk about, visualize it within a circle, on a circle, and maybe be interested in how long that line is around the circle, but also just as a portion of that circle, how much is it? So this is also just a different way to visualize that part of a whole. So this question was about the fact that depending on the size of circle you pick, obviously that line, that arc around the edge of the circle, I wasn't trying to search anything. That line along the edge of the circle, that arc on the circle can be larger or shorter. And why is this grayed out up there? It's not on my screen anymore. Okay. It can be larger or smaller, but in either case, Like the first one says it's 1/12 of this circumference. So I guess that's, let's see, 1/12 of a circumference. This is 1/12 of this circumference. 1/12 of all the way around a circle. If I say all the way around the circle is 360 degrees, 1/12 of that would be 30 degrees. And both of these then could be 30-degree angles. Now they don't actually look like 30-degree angles. They look a bit bigger. But did I do that division properly? Yeah. 360 divided into 12 pieces means the angles in both of these would be 30 based on it. It says it's 1/12. The length of that line is also 1/12 of the circumference of the circle, which we have formulas for circumference, and we could find the length of those actual lines, lengths of the arcs that are, it's called subtended, cut off by the two lines of the angle. So we can find those arc lengths if we want as a portion of the circumference, just like we could find the angle measurement where the units, generally speaking, are parts of what we consider all the way around, or parts of some other key amount, like a 90-degree angle is pretty easy to use for small angles, or acute angles. So in any case, I did want to talk about this page, which this is question 6 on this. It's a little bit of a weird configuration, but just to kind of think, we could make our units that we're measuring angles with be literally anything we wanted to. We could have them based on lots of different things. Basing on the whole circumference, we can talk about what portion of the circumference we have. But let's say that, I want to say that, well, instead of having the whole circumference have to be the thing, look at this question A. It says, visually estimate the measure of the angles in the units specified. And number 1 says, in 1/4 of the circumference. So what this is saying, what that means, and you'll see a couple of questions, not a lot, a couple of questions like this in the homework. Oh, by the way, I did want to point out, you'll see it looks a little overwhelming. Let's see if I can get in here. But in the homework, there's a bunch of things listed. There's 7.1 and 7.2 lessons due tonight, as well as 7.1 homework. All of 7.1 homework is like the stuff that we're talking about right now. It's like, which of these angles is biggest? And I don't think, it's not actually that hard. Once we've talked about some of these words that maybe seem a little bit strange or different measuring systems, it's pretty straightforward. So just kind of a review of angles. 7.1, 7.2 are things we're going to talk about today and finish today. And then 7.3 and 4 we'll be doing on Thursday. I know this red and orange is a little hard to see from a distance. But so this week we'll have 7.1 through 7.4 lessons due between Tuesday and Thursday. The homework for 7.1 is due tonight, for 2 is due Thursday, and then 3 and 4 are due next week, Tuesday night. In case you had other questions and wanted to work on those a little bit more over the weekend. Next week, though, we'll be covering the rest of Chapter 7. Well, not the rest, the next several sections. And let's see, it's chapters 7 and 8, or modules 7 and 8, I believe. That's the rest of the semester, where we're going to be talking about angles and trigonometric relationships and different ways to use those functions. But back to this, some of the questions you'll see in the 7.1 homework are about stuff like this. I just want to, so if I say that my units are 1/4 of the circumference, then that just means an angle that goes all the way around the circle would be 4 units big. So I've got 4/4 of a circumference. I don't have a name for that. Well, actually I do. I have a quadrant, right? We can talk about quadrants. 4 quadrants is all the way around. So this 6a, Roman numeral 1, I guess not Roman numeral, yeah, I guess it is. It's an I. Is 1/4 of a circumference. So if I wanted to measure this angle, and it's just drawn in a circle so that you can see how much of a circumference it is. It's like, well, that's more than 1/4 of a circumference, but less than a half, less than 2/4 of a circumference, right? So in terms of quarters of a circumference, this is about 1.5 of those, maybe. So it's not quite 2/4, so maybe 1.5. Think about questions 2 and 3, thinking about, let's see, what if I had a sixth of the circumference? Or in other words, think about dividing the circumference up into 6 parts. How many of those parts is this? Or if I don't divide it up and a unit is just one circumference, how much of a circumference is this? How much of one circumference is this? It's less than 1. And then look at B and C, which are, B is the same angle, but bigger. C is a related angle, if you notice. But take a minute, see if you can come up with some numbers of 1/4, 1/6, and 1 whole circumference for A and B. And for C, with this different angle, 1/8 of a circumference as a unit, 5/8 of a circumference as a unit, and 1 whole circumference as a unit. With these, sometimes it's maybe helpful to draw it on your own so you can subdivide it, cut your own pizza the way you want. Cut it into 6ths or 8ths or whatever so you can kind of see how this lines up with those. This is just estimate. You don't have to have any angle measuring devices here. So as I mentioned briefly earlier, A and B, if we're measuring the angles and not concerned about the length in length units, like centimeters or whatever for the arcs, notice that A and B, at least as far as I can tell, those look like they're the same angle, right? They look the same size. Kind of hard to tell because one's bigger, one's smaller. They're not right on top of one another, but that looks like the same portion of a circle, yeah? And maybe this looks approximately the same. So just visually estimating, said, well, if we're looking for how many fourths of a circle is this, if I can draw in, well, fourths of a circle would be that big. So here's 1/4, 2/4 would be there. So maybe this is 1.5 of those. Right? So that's why I said maybe it's 1.25, or 1.5 fourths of a circumference. Just estimate. It could be a little bit more, could be a little bit less, right? But if we're asked to measure in 6ths, I'm gonna not cut my pizza here. Maybe I want to divide it into 6 slices instead. So I can still cut it in half one way, but then the other way I want to cut it into, if I cut this into 6ths, maybe it looks like that. So this, where precisely this is, maybe it's halfway, maybe it's a little more, maybe it's a little less, but maybe it's just the right size to have like 1 pizza slice there. If it is, and we had 6 slices made, then that would make it this angle 2/6 of a circumference, which is not the same as 1.5 fourths of a circumference, but just visually estimating whether that's halfway into this second square, or maybe it's 1/3 of the way into the second. It's a little hard to tell. If we were talking about degree measurements, instead of quarters of circumferences and sixths of circumferences. It'd be the difference between like 120 and 135 degrees, that's a little hard to just eyeball and know exactly which one we're looking at here. But we know that this is, in terms of degrees, familiar measurements, more than 90 degrees, less than 180, kind of somewhere in between, right? And so in terms of dividing this up into fewer than 360 pieces, we can give a pretty good estimate based on, well, dividing up the circumference into 4 pieces or 6 pieces. Or not. I can say, well, if this is not divided at all, but if I just decided this was 2 1/6, I don't even know how to write, 2/6 of a circumference, otherwise known as 2/6 or 1/3 of a circumference. If it's 2/6, then it's 1/3 of a circumference, which is what C is asking about. So just kind of, 2/1/6 is 2/6. So notice this part C and its relationship to parts A and B. It's more of the circle, but what's left over out of the circle is the size that we were using before. This piece down here is about that 2/6 of the circumference, or maybe it's 1.5 fourths and 1.5 fourths is not something you normally write, but if it was 1.5 fourths, that'd be the same as 3/8, which 3/8 and 1/3 or 2/6 aren't the same number, but this is like 0.333, that's 0.325. They're pretty close, so eyeballing it, don't feel bad that, don't worry about that being, oh, that's not the same thing. It isn't, but just as an estimate, and that's all we're doing, just estimating these by visualizing, they're pretty close. So this part C in any case though, A and B are talking about this amount. C, although it's in a different location, is talking about the rest of it. Or in other words, this unshaded part in part C is the same as the shaded part, the arc we were looking at, or the angle whose size we were measuring in parts A and B. So it would be the rest of the circle, or the kind of like with complementary percentages. 40% shaded, so 60% isn't. So we're just switching what pieces we're talking about. Or if in part A and B was quarter circumference, we had 1.5 of them. Well then for part C we have the rest of 4, 2.5 of them, or 5/8 of the circumference. Now this only asks about eighths, so hey, there's the answer, 5. It's the rest of them. In terms of whole circumferences though, if these parts A and B are 1/3 of the circumference, or 3/8 of the circumference, then part C would be the rest of the circle, either 2/3 or 5/8, depending on like which estimate we were using. But it's just the rest of it, or it's like that complementary percentage. If we have one portion, the rest of it, whether we're talking percentages or fractions or even out of weird things like out of a whole circumference, these are all just relative measurements that we've been using. So let's see, there's some part that I wanted to talk about. Let's see, where was this? I think it's it's in this PowerPoint. And it's down a little bit. Let me not click through everything. All right, so don't forget that these exist, by the way, in the Rational Reasoning website. In addition to having all the different investigations that I've pulled up, there's also these PowerPoints that kind of step through the things that are said in the textbook, which is also there, but also the things that are covered in the investigations and that we talk about in class and that you'll see in your homework if you need some extra examples. Look back to those. There's a lot of good information in there because I know we don't have time to talk about every detail of every topic in class. There's more details and there's more examples specifically in a lot of these PowerPoints here. So just in terms of this, if you want to see this in more detail, this is PowerPoint number 1. Is that mine? Okay, I'm pretty sure I turned this off wherever my alarm might be because I woke up a long time ago. In terms of dividing this up into 8 equal parts or 10 equal parts and making measurements that way. Where I wanted to go with this, though, is all of these are relative measurements. And when we're talking about measuring within a circle, a unit of measure that's not nice, like in terms of degrees to talk about, but is kind of useful, is that the fact that if we're actually dealing with this circular measurement, like measuring angles as they go around a circle, which is specifically good for rotational motion, and we're going to deal a lot with rotational motion. If you have a physical circular object, like a Ferris wheel that's spinning around, or something that's traveling around a circular path, the size of that circle isn't just, oh, it doesn't matter how big the circle is, the angle's the same. Well, maybe we're talking about a physical circle, and so we're really actually interested in not just the portion of the circle, but the distances traveled around that circle as well. If we use units that match up with the units that we use to measure the size of circles, radii, the radius of a circle tells us about the size of the circle, and we can compute the circumference from that. But using the radius as a unit of measure then, we can talk about this generally, instead of saying, well, if the radius is 3, then to find the circumference I do 2 pi times 3, or it's 6 pi. Well, if the radius is r, regardless of what this r is, then the circumference is 2 pi times that r all the way around. And so going all the way around the circle, if I were to like take a radius of a circle length string and take it around, I'd have, it fits around just a little bit more than 6 times. 2 pi is just a little over 6. So thinking about measuring the circumference of a circle or splitting up a circle into not strictly portions of itself that are easy to measure, but splitting it up into, because doesn't come out evenly, like splitting a circle's circumference into eighths. There's going to be 8 equal parts. But if I want to split up the circumference of a circle into parts that are the same length as its radius, I'll get the same number of them every time. It's just not a whole number. I'll get approximately 28 of them, or about 6 1/4 of these radii would fit around the outside of a circle. So although it doesn't come out even, quite like dividing into 6 equal parts or 8 equal parts or whatever, if I divide into radius length size parts, then I always get the same number of them that fit around the circle. And it's like dividing into 6 equal parts with a little spare left over. So it's not quite like what we were doing before, but the idea of the unit of a radian, like degrees is dividing the circumference of a circle into 360 equal sized parts, if you want to think about it that way. So if there's 360 of them, would go all the way around. Or splitting, something that's like 90, splitting into 90 equal parts covers up to a right angle that's used frequently. Or you can talk about not necessarily a full circle at a time. But splitting something up into portions of the circumference of a circle that you draw, that would mean that like whenever I have a circle that's, let me draw a different circle on the board. Whenever I have a circle, regardless of how big or small it is, and the rays of that circle cut off an angle or a ray that's the same length as the radius. Whatever this radius length is, this length along the outside of the circle is. If those lengths are the same, then I'm going to call the size of that angle 1 radian. So 1 radian as an angle size is an angle that's big enough so that the arc on any circle that it's put into is the same length as the radius of that circle it's put into. So radians are weird numbers, and if you dealt with radians before in a class when you were doing like sine and cosine and stuff like that, or even like this sort of stuff, if you dealt with these before at all, it's like radians, it's a weird number. They always come in things like pi over 4 and pi over 3. The reason there's pi involved in a lot of them is because we're still talking about what portion of a circle does this cover, and 2 pi is a full circle. So a quarter of a circle would be a quarter of 2 pi, half pi. Or, you can talk about portions of a circle, how many radians it is. But 1 radian actually has a nice meaning too. It's not 1 pi radian, just 1 radian. 1 radian as an angle size is an angle that put into any circle subtends an arc or cuts off this arc that's the same length as the radius of the circle that you put it into. If I put it into a smaller circle, I want to draw those right over top of one another, but I'll draw a couple of circles. Let's see. So I'm trying to draw things that are approximately actually 1 radian in size, or making this arc length the same as that radius. Well, if I have another circle that has that same center, the radius of that smaller circle and the length of that smaller arc are still the same. So radius, large arc, same length. That's how these work. It's like similar triangles or whatever. You blow it up, it's just like I've magnified this, so if I've shrunk it down, it's still got the same relationship between the sizes of the pieces that you can see. But the angle, the specific angle that does that in radian measure is an angle with measurement 1 radian. If I were to figure out, well, how many degrees is that? Well, we've got, in order to get that in terms of how much of a circle is that, there's 2 pi radians to go all the way around. 2 pi times the radius length tells you the distance all the way around. So 2 pi radians as an angle is equivalent to 360 degrees as an angle. So if you wanted to convert that, it's just a matter of unit conversion. And there's also a bit on unit conversion at the start of this PowerPoint that this is like page 24 of. But two pi or 6.28 radians, approximately 6.28, as an angle measurement is equivalent to 360 degrees. It's also equivalent to 400 gradians, those other weird French units that I mentioned earlier. And so if I had something that, so 1 radian is equal to how many degrees? You can solve that with proportions. Just like if I said, let's see, 2.54 centimeters is 1 inch, and how many centimeters is 12.8 inches? You can do those conversions just by setting up proportions if you want to convert back and forth. Major focus of this course isn't converting back and forth between radians and degrees, but in terms of something that you have a maybe more normal picture of, like how big is a certain number of degrees, you've worked with those a lot, so it's maybe easier to picture. If you want to convert back and forth, you're welcome to. But also keep in mind that something like 1 radian is something, it looks kind of like this. It's about 1/6 of a full circle, because it's 1 out of the 2 pi is all the way around. So 1 out of 6.28 is what it is. How much this is out of a circle. Has been cut off by this. So it's like 1/6 or 17-ish% of a circle or something like that. And then if I want to say, okay, so 17% of that or 1/6 of this is about 60 degrees. 1 radian is pretty close to 60 degrees, just eyeballing it, in terms of like, how do I imagine what this is? It's pretty close. 1 radian is about 60 degrees. 2 radians is about 120 degrees, because 6 radians is just a little bit less than all the way around. 360 degrees. 6 radians takes you to all but that, there's 0.28 of a radius length left there. So 6 radians is almost the same as all the way around a circle. It's 6.28 approximately. 2 pi is all the way around. So just in terms of visualizing in radians or in radius lengths around a circle, if you can imagine this process of 1/6 of a circle and splitting it up that way, it's pretty close to that. So eyeballing things in terms of estimating in radians, you can think of 1/6 of a circle as a pretty good way to estimate. All right, let's see. I think there's one more that I wanted. No. I don't really want to do, that's all about those estimating. I thought there was one more. Nah. Let me go back to this module. Let's see. Oh, nope, that's not where I wanted to go. 7.1, not 7.7. All right. So this is just the end of this 7.1 investigation, where it describes what radians are here. It says a radian is a unit of angle measure. An angle that measures 1 radian subtends an arc that's 1 radius length of any circle centered at its vertex. And note that an arc that is 1 radius length is also 1/2 pi times as long as the circumference of the circle. So just this number 8 question. Think about in your head, and then we'll talk about this in a second, and then maybe also draw on a circle angles that are 1 radian, 2 radians, or 3.5 radians in measurement. Think about what it means for them to have those measurements, and then about how big those are on a circle. So if you could try to draw, and I have 1 on the board, but think about what the meaning of this is in terms of circles and their radius, and see if you can draw angles that approximately have 1 radian measurement, 2 radian measurement, and 3.5 radian measurement. And in terms of how exact does it need to be, see if you can make your angles terminal side, the interesting side, and in the correct quadrant. And that's close enough. What I mean by end in the correct quadrant, we draw these into circles. We usually start at the positive x-axis and then go around that way, so that we get to 90 degrees, and 180 degrees would be the negative x-axis, and so on. But measuring in different units now. So part A, 1 radian. I said, okay, well, this is maybe about 1 radian, right? So can someone say again, what does it mean in terms of the size of this angle that we're measuring at 1 radian? What does it mean to say that it's 1 relative to other parts of the circle? All right, I'll start us off. So we say that this is 1 radian in size because the angle's just big enough so that when I place it in the center, the length of the arc that's cut off is the same as 1 radius length. So a 1 radian angle cuts off or subtends an arc in any circle that is 1 radius length long. So a 1 radian angle subtends an arc on a circle that's the length of 1 radius of the circle. So So 1 radian angle, whatever circle it's put into, the length of that radius is the same as the arc that we cut off. So if I have a 2 radian angle, the arc that's subtended is going to be bigger than it would be in the same size circle with a 1 radian angle, right? It's twice as long. In fact, it should be 2 radii long. So if I were to like make a little radius length tool, let's see, that's a little bit too big. Let me fold it. All right, now the length of this paper is about 1 radius length relative to this circle. Meaning, if it were placed nicely here, curved around there, it would fit, that piece of paper's length would fit once for 1 radian. If I do it twice, I have 2 radians in length. And so there's my second one. First one is a little bit bigger than this piece of paper. So this angle is 2 radius lengths. That same radius copied twice makes an angle that's twice as big, or 2 radians in measure. If I want to do 3.5, it's going to be bigger, obviously. Not twice as big as this, but I could add on another one, maybe about there, because guess how many radians it takes to go exactly halfway around a circle? Or how many radius lengths it does? No, not 2 pi, just 1 pi, right? 2 pi radians or 2 pi radius lengths take us all the way around a circle. 2 pi radians as the angle, 2 pi radius lengths as the circumference. Goes all the way around, so pi would be halfway around, or 3 is a little bit less than that. So if I want 1, 2, 3, 4, maybe it'd be someplace down like that. So 1, 2, 3.5. Maybe it'd be someplace down here, meaning going through 1, 2, 3 full radius lengths plus a half. Now this is just a rough sketch, so maybe not particularly accurate, but I know it's going to be a little bit into that third quadrant if we started at the positive x-axis and went around counterclockwise. We'd be a little bit past 180 degrees and down into that third quadrant then, rotating that far. So 3.5 radians is an angle that I'd have to count 1, 2, 3 radius lengths plus a little bit extra, another half radius length. And again, drawing not particularly greatly accurate because I'm not good at picturing things, but it's somewhere in that third quadrant, not too far, because it takes 3.14 radians to get to here. So if I want to go to 3.5 radians, it's just a little bit farther, or that's about 0.4 of a radian down into the third quadrant, or 0.4 radius lengths along the edge of the circle farther. All right, so let's talk about measuring arc lengths and measuring angles. There's a lot of different aspects to angles that are useful. Like I said, we're going to talk about some triangle relationships, which involve, well, angles in the triangles and also the side lengths of triangles. And there's one relationship in right triangles that I'm sure you still remember Pythagorean theorem, that still works. But the angles in a triangle, those add up to, in degrees, 180, which when we're talking about triangles, we normally talk about degrees. When we're talking about circular measurement, though, and like rotation, you can talk about degrees up to a point, but depending on what you're doing, if it's repetitive motion, cyclical or periodic motion, we might get tired of talking about degrees and trying to add more and more degrees. It's easier to count by radians, actually, because if you go around a circle once in degrees, it's, like I said, 360, 720, 1080, etc. But if you go around in radians, it's 2 pi radians, 4 pi radians, 6 pi radians, like, oh, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. That's much easier to count by. You have to still know what that means, but at least it's easier to count. So in that sense, it's kind of nice. Different measurement systems are useful for different reasons. When we're talking about triangles, we're going to normally talk about angle measurements, but those triangles can also be created in the midst of a circle in order to talk about length measurements. And this is stuff that we'll talk about a little bit Thursday and then more next week. But let's say I have an angle I'm interested in, like this. And I want to talk about where this hits the edge of the circle, like as if this is my XY coordinate plane. If this is my XY coordinate point, and I want to know what's the coordinate points for that spot, well, coordinate points, we have another system of measurement. There are polar coordinates, which, if you look on here, Module 9 also says polar coordinates. Polar coordinates are based on angles and distances from the center, which is very nice for measuring circular motion also. But if I wanted to talk about this in terms of XY coordinates, that's a grid. I want to know left, right, top to bottom, how far is this from that center point? Well, the Y coordinate and the X coordinate, I could measure with horizontal and vertical lines, and if I draw them in, whether I draw it this way or the other way, I'm going to get a triangle by doing that. So just trying to talk about these measurements, and I have, I've got a hypotenuse, I've got a vertical and a horizontal leg here. So we're going to run into triangles and circles both at the same time. So it's good to be familiar with both degrees and radian measurement. But we're going to talk about the relationships between this angle, the one that we started with that went through that point, and the lengths of those segments of a triangle, which also turn into the coordinate points for this spot right here. Well, if I were someplace else, I might have some negatives involved, which I don't say the lengths of the triangle are negative, but absolute value, it's the length of the size of the triangles that we can create to try to, get to that point on the XY grid that we're used to. That's stuff that we're going to deal with, like I said, a little bit at the end of Thursday, and mostly next week we're going to be talking about triangles inside circles and the relationships between the sides and the angles and the distances and everything, and arcs, because I've got a whole bunch of different things we can measure here. We can measure this arc length. I can measure this radius, which is the same as that radius. I can measure that distance. I can measure that distance, and they're all related because they all have to fit together. There's a Pythagorean theorem that makes all the sides work a certain way, or, well, it doesn't make them work that way. They work that way, and we came up with the Pythagorean theorem because of that. But all of these pieces are interrelated, and so there's lots of different ways that we can use pieces of information we know to find those that we don't. And that's what we're going to be working on. But let's see, I was going for 7, 2. Why is this? I don't know what's up with my phone. I apologize. So let's see, there's a certain piece here that I had. All right. So this is mod 7, investigation to angle measures in context. And the first one's just measure this and find something. But question 2. So suppose we have the following angle, measures of 0.45 radians, and I want to find the length of the arc that's cut off by this small angle here in 3 different sizes of concentric circles that we have this at the center of. The radii of those circles are 2 inches, 2.4 inches, and 2.9 inches, just for examples. So what we're going to do is come up with a relationship between those. But if you know what the meaning of 0.45 radians is, we should be able to write out, or do if you have a calculator handy, a computation to figure out how long those arc lengths are. Because what, remember, a 1 radian angle subtends an arc that is 1 radius length. So what if it's not a 1 radian angle? If it's a 0.45 radian angle, then the arc that's cut off by it, or that's subtended by it, that it goes around, is going to be 0.45 radius lengths. Here, sounds better with an S now that I don't have a 1 there. 0.45 radius lengths. So what if the radius length is 2? How long is my arc? Well, if it's 0.45 radians, I've got an arc that's 0.45 radius lengths. So whatever that length is, I've got 0.45 of that, or 45% of that, if you want to think of it that way. Well, radius is 2. I've got 0.45 twos. Right? So 0.9. What were those inches? Inches. So there's 1 radius length. 0.45 of a radius length is kind of small. Let's say it's about that much. So if this is 2, the length of the radius, and this is 0.45 radians, then that length is 0.45 radius lengths, which is 0.9 in inches. Right? It's always 0.45 radius lengths if it's a 0.45 radian angle. But if I have a 2-inch radius, then I can compute the number of inches. Or if I have a 2.4-inch radius, I'm not going to draw another circle, I'm just going to change this number. If that's 2.4 inches, then the length of that is 0.45, or 45% of 2.4. I don't know what that is, but slightly bigger than 0.9. Yeah, 96. 1 point something. I want to say 1.06, but it's not going to end in a 6. I need to know. 0.45 times 2.4, 1.08 inches, not radius lengths. So it was 0.45 radius lengths. If the radius is 2.4, that's 1.08 inches. It's still 45% of it, whatever it is. So computation-wise, whatever our angles and radius lengths are, we should be able to find the arc length just by doing a quick multiplication, right? If I have my angle measured in radians, multiplied by my radius, it should tell me how many, not just how many radius lengths my angle is. I'll draw a more general one. I'll draw it like that one. Here, big angle, just so it's easier to see. So you'll see this letter used. It's not a 0, that's a theta. It's often used for generic angles, like x is used for unknown values. But value is an angle, lots of times you'll see a theta used, just for fun, because we like to use the Greek alphabet. But if I'm talking about the size of this angle in radians, and I talk about the radius in any sort of length units, inches, centimeters, miles, whatever it might be, light years, pick your favorite, then I can compute the length of this arc, which I'll call S, which is pretty common for arc length, weirdly. This arc length is just going to be, well, however much this is in radians times the radius length. So if R and S are both in length units, then S equals R times theta. The arc length is just this number of radians times how many radius length, like what's the size of my radius. If I wanted to state my arc length in radius length, it's just going to be the same as the number for theta. If it's 0.45 radius lengths, great, 0.45. But if I want to talk about in normal length units like miles, kilometers, light years, centimeters, micrometers, whatever it is, if I have the radius measured in the whatever units I want, the arc length I can get in those same sort of units by multiplying by the number of radians that my angle measures. All right, so I didn't want to talk about that. That's just messy. Is this the one I was looking at? Vertex at the center. Oh, yeah. So just in terms of the rest of it, this isn't an angle in standard position. Like I said, normally we start measuring at the positive x-axis and then go around counterclockwise, but just an angle that has a circle drawn around it so we can talk about the arcs. We can talk about, in this one, the arc that's the short way between the two rays of the angle or the long way. But if the long way is 3 pi over 2 or 3/2 pi radians, if that's that size of the angle. If I want to talk about the smaller angle, the shorter way between the two rays, in radians, how much would that be? So if I had this in standard position, that would be, all right, here's the starting place, positive x-axis. If I have 3 pi over 2, which 3 pi over 2 is the same as 3/2 pi. That's just two different ways to write the same thing. So if one of those makes more sense to you than the other in terms of looking at it, those are the same thing. Remember that for radians, all the way around is 2 pi radius lengths. 2 pi times the radius makes the circumference. All the way around is 2 pi. So 1.5 pi, 3 pi over 2. You say like, oh, well 2 pi is all the way around. 1.5 pi would be, well, 2 pi is all of it. Pi would be half of it. Pi and a half, sounds weird, but 1.5 pi would be 3/4 of the way around the circle. So this isn't drawn in that position, but the angle that we're talking about in this picture is 3 quadrants worth, or 3/4 of a full circle. 3 pi over 2, or 3/2 pi, is 3/4 of 2 pi. 1.5 is 3/4 of 2. So we've got this angle here is 3 pi over 2 radians. What's the size of this angle? Just the size of it, don't worry about like what way we're going. We're going to talk about positive and negative angles next time. But the rest of the way around would be how many radians? How many are left out? 2 pi's all the way around, and we've gone almost that far. We've got just 1/2 pi radian left. That's the rest of that angle there. So the other 1/2 pi, or pi over 2, is the rest of it, first of all. So just kind of like if I had this in degrees, I'd be like, oh, this is 270 degrees. How much is left? Oh, it's the other 90 degrees is what's left. That's all that question's about. But in terms of size of the arcs, so if this is 3 pi over 2 radians, I know if I wanted to find the length of this arc in radius lengths, it's 3 pi over 2 radius lengths. If I wanted to find how many inches it is, if I know that the radius is 12 inches, then I say, oh, it's 3 pi over 2 times 12. It's 3 pi over 2 times 12 would be the length of that. So 18 pi, 3 pi over 2 times 12, like over 1. You can do some reducing. 18 pi, and that would be in inches, as opposed to 3 pi over 2, which is in radius lengths. Be 18 pi inches to go that 3/4 of the way around the circle, or to travel through 3 pi over 2 radians along the edge of a circle that has a 12-inch radius. Or if I wanted to estimate this, that's about 18 times 3, a little bit more than that. So 54, 55 inches, a little bit more than 54 inches. Because pi isn't just it's not a unit. Pi is 3.14 approximately. So if I wanted to say this in a decimal number of inches, it'd be 54, 55 something inches to travel that far around the circle. If I want to know how far around the circle there is still to go, I've got 1/2 pi of an angle yet, right? The rest of the circumference of the circle, or 1/2 pi times the radius length, 1/2 pi times 12, or 6 pi would be the length of this in inches, or like 18 something inches. 6 pi inches is about 6 times 3 inches, just in terms of mentally. Just remember that pi is not a unit, it's just a number. It's never a unit. Just lots of times when we're measuring angles in terms of radians, if we stop at these key quadrant points, we're going to have multiples of pi, just because 2 pi is all the way around. So if we're a nice even fraction of all the way around, we might write that fraction in terms of pi. Instead of 1 radius length around, we can just talk about being a 1 radian, or 2 radians as 2 radius lengths around, which is about 2/6, but not quite. So in terms of things to think about, your assignments for tonight, like I said, there's 7.1 and 7.2 lessons, which are about radians and degrees and angles, and arc lengths are thrown in there more in section 7.2. But the relationships between these things and how to estimate based on number of circumferences, or fraction of a circumference, or fractions of a radius around a circle, how to go just thinking about circles instead of here's a bunch of formulas, plug in some numbers and go. I just want you to think about how these pieces of circles and the angle measurements within a circle are related to one another. It'll give you a good sense about what it is that we're doing when we get into more complex formulas that relate more and more pieces and more different measurements, as long as you understand what all those measurements are for, what they're all telling us about the figures that we're dealing with. And sometimes they'll be fixed figures, and sometimes we'll have figures that are moving. In order to track motion in circles, we're going to be using trig functions. But we can also just relate the pieces of a fixed triangle by using trig functions. And by trig functions, I mean things like sine, cosine, tangent, and their reciprocals. But if you know like sine and tangent, then the rest of them we've got, because those two kind of cover everything in one way or another. But in any case, that's it for today. Think about those, take a look at, make sure you work on these assignments tonight. Like I said, that it looks like it's a lot, but they're pretty short, and some of it's like, which of these is the biggest angle? So I hope those are pretty easy too. The point of that isn't to be condescending, it's because you have to think about what's meant by size of angle, because it really is kind of a weird thing to think about, as opposed to like size of a room. Size of an angle is a weird measurement. It's always relative to something. All right, thanks guys.